Hello, and welcome to the Excitable Cells as Dynamical Systems module of the Introduction to Dynamical Systems course, Part 1, Neurons and the Hodgkin-Huxley formalism. My name is Alexey Braja and I'm from Moscow State University. In this lecture, I'll talk about the behavior or excitability of neurons and how to describe it with Hodgkin-Huxley formalism. So, if we have a neuron, let me draw it here. So if we have a typical pyramidal neuron of a cortex with its apical and basal dendrites and an axon, and if we poke it with a sharp glass electrode, we can measure the transmembrane potential, that is the difference between the inside and the outside voltage of the neuron. And if we measure it in time, we can observe the following. If the neuron is resting, the membrane potential doesn't change. But if we stimulate it with a short pulse of current or voltage, then we can observe a stereotypical waveform or change in membrane potential that is called spike or action potential. So if after stimulation the neuron returns to the resting state, that is called an excitable neuron or excitable system. So after a large excursion in a phase plane, our system returns to the stable equilibrium. In a different case, a neuron can be generating action potentials with a constant frequency or periodically. So that would be called periodic spiking. And yet again, a different set of parameters, the neuron can generate batches or bursts of spikes. That would be called periodic bursting. Now, starting from Hodgkin, it has been realized that different neurons have very different excitability properties. So some neurons, if stimulated with pulses of different amplitude, would produce periodic spiking at different frequencies. So in fact, they encode, so if this is the frequency of spiking, they encode the intensity of stimulation with the frequency of spiking. At low intensity, low frequency spiking, and at high intensity, high frequency spiking. And these neurons were termed class 1 by Hodgkin. Other neurons, also present in the nervous system, in the CNS, behave quite differently. When stimulated with low amplitude stimuli, they produced either nothing or just a few action potentials at the onset of the stimulus, but then they didn't sustain periodic spiking. Only at higher stimulation currents, they would flip to sustained spiking, but in a very narrow frequency range. So these neurons actually didn't encode the intensity of stimulation with the frequency of spiking. So this type was called class 2 by Hodgkin, and yet again another class of neurons couldn't sustain periodic spiking at all, no matter how high the stimulation current is. And these neurons were termed class 3 by Hodgkin. And in fact, in our CNS, there are neurons that behave just like that. For example, octopus neurons of the ventral cochlear nucleus can't sustain periodic spiking at all. So of the VCN, ventral cochlear nucleus. Now, to understand why different neurons have different excitability properties and what are the mechanisms that provide for these differences, how can these differences be explained, and how you can build a description of a neuron or a network of neurons from a Lego blocks of different kinds of ion currents, channels, and so on, one needs theory. So here is that where theoretical neuroscience actually complements the experimental neuroscience, and the whole thing of how much there is crosstalk between experimental neuroscience and theoretical neuroscience, and if there are any problems or traction in this crosstalk, can be found in a set of interviews on YouTube with hashtag Theory Matters, where leading neuroscientists for both experimental and theoretical neuroscience discuss why theoretical neuroscience matters for experimental neuroscience and vice versa, and why the Hodgkin-Huxley formalism, modeling neurons, is so important. And in this lecture, we will see how the activity of a neuron, a change in its membrane potential, can be described by currents and equivalent electric circuits. So we'll describe how Hodgkin and Huxley came up with their model, and how this model can be used further to describe other neurons with other currents at different conditions. So a neuron is of course delimited by its plasma membrane. I'll draw a cartoon of it here. So it's a bilayer lipid membrane, which has specific proteins called ion channels, which can be selective and, for example, only allow sodium currents to go in or out of the cell, and the direction of the flow is thermodynamically driven, and mostly sodium goes into the cell because there is much more sodium in outside than there is in inside, and also because the negative part of the membrane is charged, the inside part of the membrane is charged negatively than the outside. So I'll write it down here. So this is the outside and this is the inside of the membrane of the neuron. Besides sodium channels, there are other, of course. For example, specific to potassium ions that only allow potassium ions to go out of the cell or in the cell, but mostly out, because there is so much more potassium inside the cell than there is outside. So the direction of potassium current is mainly outwards. Of course, there should be a mechanism that allows to keep the resting concentrations of the potassium or sodium ions inside and outside of the cell, and this is brought about by the sodium-potassium pump, which pumps 2 potassium ions in the cell and 3 sodium currents outside the cell, and it spans 1 molecule of ATP for this cycle. So it depends on external energy to do that, because it does that in the opposite direction that the difference in electrochemical potentials try to force it to. So the flow of sodium and potassium currents through the channels is defined by the gradient of electrochemical potential for sodium and potassium, and the pump spends the energy, that would be actually pump, spends the energy to drive the ions in a energetically unfavorable directions. Now that's again, that's of course a pump. Right. Now, of course, we can also have a sharp glass electrode, and that could be also used to drive some current through the membrane. If we look at the membrane at a different angle and say this is actually an electrical circuit, so we can describe all the entities as electrical elements. like membrane is actually a capacitance. Now each of the currents or each of the ion channels is actually a variable resistance, also coupled to a battery because of the concentrational gradients. So that would be a potassium and that would be a sodium. Ion channels. Then there is a pump, which is actually an electrical current source because it drives 2 potassium ions and 3 sodium ions. So that would be our pump. I got it right now. And our stimulation electrode can also be regarded as a current source. So this is the electrical circuit, equivalent electrical circuit. Now if we use some specific chemicals, blockers or toxins, and block all the specific channels or block all the proteins that allow ions to go in and out of the cell, then what we observe is just passive electrical properties of the membrane. And if we make a rectangular pulse in the applied current, so that would be our applied current, and then we will observe charging of the capacitor and then of course discharging with a characteristic time scale, of course being the product of membrane resistance to membrane capacitance. Now what Hodgkin and Huxley did was that they used a specific experimental protocol to measure the currents through the cell at different voltages of the neuronal membrane, which is called voltage clamp. So they could set the membrane potential at some common value and see how currents through the membrane develop over time. What they used as a preparation was the giant squid axon, and actually it's the normal squid with a giant axon. And this axon is so huge you could see it with a naked eye and poke it with the long sharp electrodes, and you can use a pair of electrodes to measure the transmembrane voltage like this. So the output of this amplifier is actually the difference between the outside and the outside of the membrane. So you measure that, and then you use that value and compare it to the value you set and you want to clamp your membrane at. And what you also do, you use another pair of electrodes, the command or the stimulation electrodes, to compensate for any difference between our desired voltage and the measured voltage. It's also normally it's grounded. So at any time the transmembrane potential is constant, but what you measure is the current you need to pass through the membrane so as to keep the membrane constant or clamped, hence the name voltage clamp. And now what brought Hodgkin and Huxley the Nobel Prize was the idea that they could separate the currents mediated by potassium ions and currents mediated by sodium currents by using blockers or ion substitutions. So the main breakthrough was to measure independently the potassium and sodium currents and show that they have different kinetics, different dynamics. And this is how it looked like. So, for example, if this would be time, and you start from holding the membrane at the resting state where there is no net current, so through the membrane. So that would be your voltage. And then you make a sudden jump. For example, V rest, let me call it rest. V rest plus, let's say, I don't know, 25 millivolts. Then what you see is you get a gradual increase in the potassium current, and then it saturates. If you make a larger voltage step, then what you observe is that first the dynamics is faster, and then the steady state current is also larger. And if you have a lower stimulation current, like this for example, then you have a slower kinetics and a lower steady state current. So from this experiment, what you actually extract is the characteristic time scale as a function of membrane voltage, and the steady state current is the function of membrane voltage. Now, you can think that instantaneous current is actually ohmic. So you could describe your potassium current as the conductance times the difference between the current transmembrane potential and the reversal current for potassium. Let me say let me denote it with E. You could call it an equilibrium potential, an equilibrium, or the reversal potential for potassium ion. Now from this, you can deduce that you could say that your G of K is first goes from some value to the steady state value over time. So if this is time, then it goes to a steady state value. And what you also can think of is that actually you have a maximum, absolutely maximum conductance, and denoted with G bar, times the fraction of open gates, which you call N. So Hodgkin and Huxley thought that in the membrane there can be gates allowing potassium ions to go through the membrane, and then the fraction of open gates determines how big is the conductance for the potassium ions, and also the fraction of open gates is also related to the probability of finding each gate open. So what the idea was is that you can describe the conductance of the potassium ions as the G maximum conductance at the absolutely highest stimulus current times the probability of finding open gates. Now we call them channels. So then you could fit an experimental data to find out how the steady state fraction of open channels depends on membrane voltage, and how the time constant depends on voltage. So from the set of such experiments and transforming the equation from measured current to measured conductance and dividing it by the absolutely maximum conductance, you'll get something like this. So if this is voltage, then you get approximately the following relation for the steady state activation gate of the potassium ion, potassium channel. And also, if you measure the time constant, then it will be something like this. So that would be tau n, depending on V. Now, from these two parameters, you can build a dynamical model to describe the kinetics of the activation gate for the potassium channel, which is, of course, very simple. So this implies very simple kinetics. You start with some value. For the given transmembrane potential, you have a steady state value and a tau or time scale. You reach this steady state. It's very simple linear kinetics. What Hodgkin-Huxley also thought was, it is also possible to describe the gates as being open and closed, and there could be rates of opening and closing the gate. So if you say that the gate can be open or closed, and you term the opening rate as alpha and closing rate as beta, and both of which are functions of transmembrane voltage, then you can write an equivalent linear model for changing in activation gates of the potassium current is the following. So it's alpha times 1 minus n, because if n is a fraction of open channels, or open gates, then 1 minus n is a fraction of closed channels, minus the rate of closing, and is of course times n. You can see that in fact both expressions are interchangeable, and this can be left as an exercise to show that alpha and beta can be derived as expressions of tau n and infinity, and vice versa. But if you look at the described dynamics, what you will observe is that it actually, in this formulation, doesn't describe the experiment all too well, because if you just use this expression, then you won't get any inflection points. Your dynamics will be also always starting from 0 and always convex. What you actually want is to, if you actually want to have an inflection like this in the kinetics, then you might think that there is some kind of cooperativity. For example, if the gates are clustered and they only allow passing potassium ions when all the 4 gates or 3 gates or any number of gates open, then you can use some kind of cooperativity coefficient here, and from the experiment on the squid axon, it just happened that the best fit was achieved if the cooperativity coefficients was taken to be 4, also 4 gates in a cluster in this model. But it doesn't have to be so. In different neurons from different species, there are potassium currents with different values of this cooperativity coefficient, and even without it. So different potassium currents can be described with different cooperativity coefficients. Now, the situation with the sodium current is in fact similar, but a little bit more complicated. In a similar experiment, if you have a step in voltage from the resting state to V rest plus some addition like 60 millivolt, what you observe is first your sodium conductance or sodium current, and there shouldn't be, sodium current rises very fast, but then it also goes down. Why does it happen? What Hodgkin and Huxley thought would explain this experiment is that there are actually two gates. One responsible for activating or opening the channel, and the other gates responsible for inactivating the channel or the gate, the current. So what they described the sodium current with was maximum probability times activation gates M times inactivation gates H times V minus V E, actually E sodium. Now the product of these two gate variables is the fraction of open channels, and if you use clever experiments with paired pulses or two-step protocols, like if you hold your potential at very low for example it's minus 70 and that minus 120, membrane potentials, and then you jump to a higher membrane, higher potential, then what you get is, for example, when you have your neuron at very low, at very hyperpolarized state, all the inactivation gates become open and you see the large response. And if you hold the potential at a less hyperpolarized state, then you get a lower response to the jump. So anyways, if you measure the dependence of the steady state activation gates M, what you'll get is a curve similar to the activation of the potassium channel. But if you look at the activation of the inactivation, if you look at the inactivation gates H, you'll get the opposite. So the more hyperpolarized membrane, the more inactivation gates are open, but the less activation gates are open. But if you move to the depolarized state, more activation gates M will be open and less inactivation gates will be open. So at the steady state, if you go to depolarized membrane potentials, at the steady state you get very low sodium conductance. But the trick is that the inactivation is much slower than activation. So if you draw the time constants, what you get is that if your tau H is something like this, then your MH is very much lower, which means much faster dynamics. So that's why if you depolarize the cell, the sodium current rapidly increases because the activation gates are much faster, but then inactivation gates catch on, so to speak, and they inactivate the sodium current. Well, this all leads us to the final equations of the Hodgkin-Huxley formalism for squid neuron, for squid axon. So what the Hodgkin-Huxley formalism actually states is that given a neuron, you can describe the changes in its membrane potential via the sum of different specific currents, namely, for example, sodium current, the potassium current, and also there is an addition, which is a small current which doesn't depend on transmembrane potential, which is called leakage current. And if you have a different neuron, you may have different kinds of sodium and potassium currents, or even mixed cation currents, which allow both sodium and potassium, or even sodium, potassium, and calcium go in and out of the cell. But still, the change in the membrane potential is governed by the sum of different independent currents, and each current can be described as its maximum conductance times the probability of finding this current in an open state, or fraction of open channels, times the current membrane potential minus the reversal potential for this ion, or for this current. Now, the fraction of open ion channels or open gates can be a product of two different kinds of gating variables, one responsible for activation and one responsible for inactivation of this current. The dynamics of these gating variables can be cooperative, and it is reflected in a power you raise the gating variable to. It's very simple. For example, if the potassium current can be only active, so to speak, if all four of the gates are open, then the probability of having the current is proportional to n to the power 4, just by combinatorics. Now, the dynamics of the gating variables is described by simple linear equations with opening and closing rates depending on the membrane potential. So the opening rates is alpha and the closing rate is beta, and these values are fits to the experimental data by Hodgkin and Huxley. They can be looked up in the literature and so on. So just to reiterate, the change in membrane potential is driven by the sum of different currents, and each current is instantaneously ohmic. And each instantaneous conductance is maximum conductance times fraction of open channels, which can be factored to activation and inactivation gating variables, each having fairly simple dynamics. And the gating kinetics, the rates of opening and closing of the gates, depend on membrane voltage. Now, there is a whole zoo of different kinds of ion currents in neurons from different species or from different nervous system areas. And for example, there well can be sodium currents without inactivation, and they're called persistent sodium currents, where H is always equal to 1. And there can also be different kinds of potassium channels, for example, without any cooperativeness, or transient potassium currents, which also can have inactivation gates. But the formalism remains the same. You can describe each current. You measure each independent current you can measure in a neuron with this formalism. So the steady state values for the gating variables, for example M, N, and H, they depend on the membrane voltage, and so do the rates of change, or the characteristic timescales of the variables. And you can see that by far the activation of the sodium channel is the fastest because it has the smallest tau. So that would be tau m. And inactivation of the sodium channels is by far the slowest. What it means in practical applications is that it is often possible to think of m of t as like approximately stable or approximately the same as its steady state value. So so say that the sodium kinetics is instantaneous. We don't want to describe it, because what is the difference if your membrane potential looks something like that, or it looks maybe something like this? It's practically the same if you use the instantaneous sodium channel instead of describing its actual activation. Now, if we build a model of a Hodgkin-Huxley neuron and see how it responds to current pulses, we can see that low stimulus leads to subthreshold responses, and higher stimulus can lead to a single action potential, and even higher stimulus can lead to sustained spiking. And it's important to observe that if you zoom this up, the return to the resting state is actually oscillatory. So it has damped oscillations, and it will be important in the next video. So please know that. Hodgkin-Huxley formalism also allows to describe the temperature dependence of the kinetics. I didn't specify the details how it's done, but it is possible. And for example, the actual measurements for the squid axon were done in bath solution of 6 degrees centigrade, because that's where the squids like to dwell. But of course, if the same formalism is used to describe mammalian neurons, the temperature has to be scaled, and of course all the rates, opening and closing rates of the gates, should be scaled with temperature. And for example, this is how the same model behaves at temperature 23 centigrade. So we see that at high temperature, the spiking rate is higher and the amplitude of the spike is lower, and so is the duration of the spike, which is substantially smaller at higher temperatures. Now, also in modeling, it is frequently desirable to parameterize the kinetics of the gating variables with the simpler functions. For example, a tau could be described as a simple Gaussian function with some mean value and standard deviation. And also a gating variable, for example, for an n, or activation of the potassium current, can be described as a simple sigmoidal function called Boltzmann function. So these of course are functions of V transmembrane potential. So it's 1 over 1 plus exponent of inflection point minus V divided by K, where K is inversely proportional to the slope. So this is how it looks like, this function. So that would be inflection point, and inversely proportional to the slope is K. And later on in the next video, we'll use this kind of parameterization to simplify the model. And so in the next video, we will use the simple model derived from the Hodgkin-Huxley formalism, which is called persistent sodium plus potassium current model, which means that the sodium kinetics will be, first, it will be instantaneous. So m of t will also always be the steady state value. And H will be always equal to 1, so there is no inactivation of the sodium current in this model. So all the slow kinetics of the models will be described by the conductance of the potassium channel.